The work presented below is titled Use of Industrial Glass Waste in Obtaining an Alternative Activator Used in the Preparation of an Alkali-Activated Cement. This project was carried out at the Institute of Engineering and the Faculty of Chemistry of the National Autonomous University of Mexico. Currently, reducing carbon dioxide emissions and solid waste are some of the global challenges. In this context, the cement industry is the second industry with the highest emission of carbon dioxide into the atmosphere, responsible for 5 to 8% of the emissions of this greenhouse gas, and is the second most consumed material in the world, only behind of the water. For its part, the glass industry annually produces around 130 million tons, of which only 27 million tons are recycled. So about 80% of the glass goes to landfills. Similarly, the generation of electrical energy from thermoelectric plants emits gases and other pollutants such as sulfur and nitrogen oxides, as well as particles and solid waste like fly ashes. Forecasts estimate an increase of 30% in the production of electrical energy from coal, and it is expected that this will be the case for at least the next 30 to 50 years. In order to reduce pollutant and solid waste emissions, activated alkali cements have been considered as a viable alternative due to their lower energy demand and environmental impact, with good mechanical performance and durability. These materials are obtained from the combination of an aluminosilicate such as metallurgical slag, fly ash, or silica fume, with an alkaline source called activator. The mixture of sodium hydroxide with sodium silicate is the most widely used activator. However, its manufacture requires high temperatures, and approximately 1.95 kilograms of carbon dioxide are emitted per kilogram of hydroxide and 1.50 kilograms of carbon dioxide per kilogram of silicate. Therefore, the search for alternative activators with less environmental impact arises, so this work presents the reuse of industrial glass waste as a raw material in obtaining an alkaline activator. The methodology used throughout this research can be divided into two stages. The first stage is obtaining and conditioning the raw material. In it, the fly ash was obtained from the Federal Electricity Commission thermoelectric plant, while the glass waste from the Pavisa Group. The materials went through a process of washing, in the case of glass, and quartering, in the case of ashes. Later, both were dried, ground and sieved to obtain particle sizes of 45 microns in the fly ash and 38 and 75 microns in the glass residues. Finally, a physicochemical and microstructural characterization was carried out. In the second stage, a series of experiments are carried out with a reaction in which the glasses crushed at 38 and 75 microns are added to a 10 molar sodium hydroxide solution at different conditions ranging from 4 to 8 hours and from 60 to 90 degrees centigrade. Once the reaction is finished, the solution obtained is filtered and analyzed by ICP. Finally, with the solution that has obtained a greater amount of dissolved silicon, a mixture with fly ash is created to prepare a paste within radius of 0.3 and make an activated alkali cement whose mechanical resistance will finally be measured by compression. It was observed that the fly ashes have as main oxides, silicon, aluminum and iron oxides, and to a lesser extent calcium and magnesium oxide. According to the specifications of the ASTM C618 standard, the fly ash corresponds to a type F ash. Chemical analysis by XRF shows that glasses are made up of silicon oxide, sodium oxide, and calcium oxide to a greater extent, and iron oxide to a lesser extent. This indicated that the glass waste is the sodium-calcium type, and that its high silicon content makes it viable to be used as a source of silicon. X-ray diffraction analysis of the fly ashes confirmed the presence of amorphous material, identified in the diffractogram by the lifting of the baseline and the wide halo of 15 to 35 degrees of 2 theta. Likewise, the characteristic signals of quartz, mullite and magnetite were observed. The presence of amorphous material in a higher proportion is an indication of the reactivity of the fly ash, which is important for the activation of the fly ashes in an alkaline medium. XRD analysis confirmed its amorphous character or low structural order, without the presence of crystalline material. The 20 to 40 degrees wide halo of 2 theta in the diffractogram is characteristic of its amorphous nature. Its position and maximum intensity are related to the calcium content present in the glass. The FTR spectrum of fly ashes exhibits two main broad and intense bands, characteristic of internal vibrations of silicon and aluminum tetrahedra. The characteristic bands of quartz, mullite and amorphous material overlap in the 1200 to 900 range, generating the broad and intense band in the FTR spectrum of fly ashes. Gaussian deconvolution of the spectrum revealed 5 fundamental signals. The series of lower intensity bands located at 1109, 790 to 780 and 694 are characteristic of quartz. While mullite is responsible for the bands at 1173 and 560 to 550, associated with octahedral aluminum. The bands located at 984 and 928 were attributed to the amorphous phase. In this table we can see the amount of silicon oxide and sodium oxide that was dissolved in the activating solution, and it is observed that sample with the highest amount of dissolved silicon was number 1, which was prepared at 90 degrees Celsius for 8 hours, and the glass with a particle size of 38 microns. The results show that the increase in the time and temperature, as well as the decrease of particle size improvement the silicon dissolution in the industrial glass waste. Finally, with the activator with the highest ratio, an activated alkali cement was manufactured and its mechanical resistance to compression was measured after 7 days of curing. This was compared with another activated alkali cement manufactured from a mixture of hydroxide and silicate, and it was observed that materials with very similar strengths are obtained, the cement created from the alternative solution being slightly higher. The results showed that silicon from glass waste dissolved in sodium hydroxide solution can induce the same effects as the silicon in water glass, so can be used as activators. The best conditions of solubility of industrial glasses waste were a treatment 90 degrees Celsius, a reaction time of 8 hours, and particle size of 38 microns. The behavior of the pastes of alkali-activated cement in terms of strength compressive was comparable to the performance observed in pastes prepared with conventional activator.